We're going to talk about section 6.3, integration by parts. We talked about this some last year, but it was not a AB topic, so you wouldn't have seen it on the AP exam, but it is a BC topic, so you will definitely see it on your exam this year. So first, let's explore where it comes from. So integration by parts essentially is how do you integrate something, a derivative that came from the product rule. So we write this kind of using our, first we'll do it with a long notation, then we'll get to the kind of shorthand notation. So we're thinking of u and v as functions of x. So using our product rule, we would get the first u of x times the derivative of the second dv dx plus the second v of x times the derivative of the first du dx. But we're going to write this in more symbolic notation. That is, we're going to write that as the derivative of uv is going to be, and we'll write that as u dv plus the integral, not the integral yet, v du. Okay, now what we can do is imagine that if these two are equal to each other, then their integrals should also be equal to each other. And so what this leads to is that the integral of the derivative is going to be just the uv, and that is going to equal, we're going to write it as the integral of, and I don't think I wrote that one right. Let me go back. This should have been u dv. I think I said dv but wrote dx. So u dv plus v du. So that's going to be the integral of u dv plus the integral of v du. So then we solve for this one. We leave this integral and move that one to the other side. And so this leads to the integral of u dv is equal to uv minus the integral of v du. And this is our integration by parts. What we try to do is identify an integral that we can't do any other way and try to name part of it u, the other part dv, so that we can account for everything in the integrand. Then we can follow this pattern, and then the hope is that we replace an integral that we couldn't do, u dv, with one that we can or we can eventually get. So sometimes there's this kind of acronym that helps people remember. The hard part is choosing what's going to be u and what's going to be dv. So there is, if it helps, kind of an acronym to help you decide what to choose for u. So when you choose what the u is going to be, your order of choices is first a logarithm. So if there is a logarithm in the integrand, we're going to call that u and the rest of it dv. The second choice is an inverse trig function. And the third choice is going to be any polynomial. So those are all good choices for u. Then it gets to be less desirable, but an exponential, if we haven't encountered anything else, any of the 1 through 3, then if there's an exponential, it's okay to call that u. And our last choice is going to be a trig function. So we can do it that way, but it's not always a great choice. Okay, so using this, let's see what we can do here. Here's an integral that we don't know how to do. So we're going to do integration by parts. We're going to pick what is u and what is dv. So using our Lipit, we see that we don't have a logarithm, we don't have an inverse trig function, but we do have a polynomial. That's x. So we're going to call that u. The rest of it then becomes our dv. So then we have to compute a du, and that's going to be just 1 or 1 dx. And we have to find a v, that is we have to integrate or find an antiderivative of cosine. and so that is going to be sine x. Then what we're going to do is use our pattern, that is our integral of u dv is going to be uv minus the integral of v du. So our u times v is going to be x times sine x, and then we go minus the integral of v du, which is sine x dx. And this we would have to consider a success because now this is an integral that we can do, whereas we couldn't have done the original. So we do that integral. And so we're going to get the x sine x that we already got. The integral of sine x is going to be, let's see, that's going to be a negative cosine of x. And so with the minus sign in front, that's going to give us cosine x plus c. So we get our final answer is our integral is x sine x plus cosine of x plus c. Okay, now there's some other little tricks that come along, of course, and so I'm going to slide this up a little bit. So one other thing that we may encounter is repeated use of integration by parts. So that means what we have here is an integral that we can't do. So again, we're thinking limit. So we're going to say the first thing that we encounter for a choice of u is going to be our polynomial, which is x squared. And that means the rest of the integrand is going to be our dv. So we call that sine x dx. So du is going to be 2x dx, and the v is going to be an integral of sine of x, which is going to be a negative cosine of x. So we get our uv minus the integral of v du is our pattern. So we are going to get here u times v is going to be a negative x squared cosine x minus the integral of v du, but our v and du has another negative sign, so that's going to become plus, and then we'll get a 2x cosine of x dx. But we can't solve this directly yet either. So we do it again. We leave this part as it is, but now we're going to pick a new u and dv for this integrand. So again, using u as the polynomial, dv is going to be the cosine, so du is going to be 2 dx, and v, the integral of cosine, is a sine of x. So we've got the negative x squared cosine x that we got originally, and then we're going to get a plus. Now a new u dv is going to be 2x sine x, and then minus the integral of v du, which is now a 2 sine x. And this, the good news is, we can actually evaluate or integrate. So we're going to have our negative x squared cosine of x plus 2x sine of x. And now we're going to get the integral of sine is going to be a negative cosine. So that's going to be a plus 2 cosine x plus c. Kind of crazy. Okay, so let's see how we can use integration by parts to solve a differential equation. So here is our differential equation. dy dx is equal to 3x squared natural log x, and we have the initial condition that y is 2 and x is 1. So this is what we would call an exact differential equation because we have the derivative already isolated by itself. So we can just integrate both sides. So the left side is straightforward enough. That's the integral of the derivative of y is just y. Now the second integral is going to require integration by parts. So we need to figure out what is the u and what is the dv. Now remember, in our limit, the first choice was going to be to make u the logarithm. So we're going to call u our natural log x, and our dv is going to be then a 3x squared. So the du, the derivative of natural log x, is 1 over x dx, and v, the integral of 3x squared, is x cubed. So we're going to get our uv minus the integral of v du, and so the u times v is going to be x cubed natural log x minus the integral of v du is going to be our x cubed times a 1 over x. And so that's going to become minus the integral of just x squared dx, which is going to be minus 1/3 x cubed. We still have our x cubed natural log x plus c is our function, but that's the general solution to our differential equation. So now we're going to use our initial condition, that is that y is 2 when x is 1. So doing that, we're going to put in 2 for the y, and since the natural log of 1 is 0, that's going to all drop out. Plugging in the 1 for x to the minus 1/3 x cubed is going to be a minus 1/3 plus c. So adding the 1/3 over is 2 and 1/3, or 7/3, either way, whichever way you want to call it. That's our c. So we get finally our solution to this initial value problem is going to be our x cubed natural log x minus 1/3 x cubed, and then we're going to get a plus 7/3 tacked on to the end. So we just had to use our integration by parts to do that integral. The next one is kind of crazy. So this is where we're going to solve for an unknown integral. So you have to be a little patient here. So if we're using our limits, there's not any real great choice for this. So if we use that as our guide, we don't have a logarithm, we don't have an inverse trig function, we don't even have a polynomial. First thing we encounter is our exponential. So let's just go with that. We're going to say u is going to be our exponential e to the 2x. That means our dv is going to be cosine of x dx. So we're going to get du is going to be 2e to the 2x, and v, the integral of cosine, is going to be sine x. So far what we've got is uv is going to be e to the 2x sine of x minus the integral of v du is going to be a 2e to the 2x sine x dx. Well, as you can see, that's not really any kind of improvement over where we were before. But we're going to be patient and proceed on faith. So now we're going to make our second choice. Again, this time we're going to go u is going to be 2e to the 2x, and our dv is going to be the sine of x dx. So du is going to be now a 4e to the 2x, and our v is going to be the function that's an integral of sine x is going to be a negative cosine of x. Okay, let's see where we are. I'm going to come back over here to the left. So far, we have our original, that integral of e to the 2x cosine of x dx was equal to our first uv, which was e to the 2x sine x. And then we have minus, and now we've got a uv. So let me go minus our uv is going to be a negative 2e to the 2x cosine x minus the integral of v du, which is going to be a 4, let's see, v du. So we're going to have another negative sign is going to make that plus. So 4e to the 2x cosine x dx. Now, we might look at this and be like, oh my goodness, that's exactly where we started. Look at that, e to the 2x and a cosine x. This is actually a good thing, because what we're going to do, strangely enough, is I'm going to first distribute that minus sign. So the negative times the minus 2e to the 2x cosine x will be a plus 2e to the 2x cosine x. And then we're going to get a minus 4. I'm going to pull that outside the integral, e to the 2x cosine x dx. Remember, that's equal to the integral of e to the 2x cosine x dx. So we now think like algebra, and these are the same. So I'm going to add 4 of those integrals to that left side, and that's going to make that be 5 of the integral of e to the 2x cosine x dx's are equal to e to the 2x sine x plus 2e to the 2x cosine x. And now I'm just going to solve for that integral by dividing by 5. Yes, I know this seems very unsatisfying, but we're getting that the integral of e to the 2x cosine x dx is going to be e to the 2x sine x plus 2e to the 2x cosine x all over 5, and then the most missed plus constant of integration of any problem will be that one. Crazy. Let's go to the panel and slide. Oops. Let me erase that for a moment and see if I can slide this panel up a little bit. Okay, right there. So this now is known as tabular integration. And if you saw the movie Stand and Deliver, you see them do that in there. And I'll try to show you a clip in class of that if I can get it to work. So this is, this really, you don't need to know this for the AP exam. Back in the day when pre-modern era, which is when graphing calculators became available, sometimes they did stuff like this where it was really, we would say, computation intense. And so they would regularly get problems like we're going to see here. And so having this strategy or technique was kind of handy, but I would be very surprised if you ever saw a problem on your AP exam that would require something like this. So anyway, let's see how it looks. It's a way of organizing and doing our integration by parts, but it's really only useful in a special kind of instances where the f of x is our choice for u is going to eventually differentiate to 0, and the other part, the dv part, we can actually do those integrals without too much pain and suffering. So here's what's going to look like. We're going to start with f and its derivatives. So we're going to go x squared, whoops, didn't mean for that to happen. Let me make that a little bit bigger, and let me try that over again. So our f is x squared, its derivative is 2x, that derivative is 2, and we do this until we get to 0. Then over here, we're going to do our g of x and then each successive integral. Now, this was a good choice because the integrals are just the same thing each time. They're really easy to do. Then what we do is we're going to go diagonally. So we're going to go this times this, and we're going to, by plus I mean we're going to keep that same sign. So we're going to, and then we're going to go down this way, and we'll subtract that, and we'll go down this way and add that. We would do this as many times as we want until we get to where the derivative disappears. So on Stand and Deliver, it's pretty dramatic, this scene, because he goes tick, tack, toe, see? And anyway, so you get the x squared times e to the x, and then minus, that's the diagonal minus, 2x e to the x, and then plus the 2e to the x, and then tack on a plus c to the end. So that's how that works. Well, let's see if we can do it on this next example. So I'm going to try to slide this up again, and we'll see if we can kind of make our tables over here. So I'm going to say here's f, and here's g, and we're going to choose x cubed, and then we'll do its successive derivatives. So that'll be 3x squared, 6x, 6, finally getting to 0. We're going to start with sine of x. Its integral is going to be a negative cosine x. Its integral is going to be a negative sine x. Its integral is going to be back to a cosine of x, and its integral is going to be a sine of x. Whew. Now we're going to go down, adding, and then down, subtracting, and then down, adding again, and then down, subtracting again. So tick-tack-toe. So we're going to get then x cubed That's going to be a negative cosine in there. So negative x cubed cosine x, and then a minus, and then we're going to get another negative, makes that plus 3x squared sine of x. And then we're going to get, we're up to a plus 6x cosine x, and then a minus 6 sine x, and then a plus c at the end. There you have it. Kind of cool. Okay, last thing. Integrals where dv is dx. So this is actually an integration by parts problem. May be hard to recognize until you've had some practice. So remember, if we're using our limit, we're going to say that we don't have a logarithm, but we do have an inverse trig function. So we're going to choose u to be the arc sine of x, and that means the dv is just dx. That's the hard part to see. Our dv is just 1 in effect. So the du, if we remember the derivative of arc sine of x, and who could not remember that, is going to be 1 over square root of 1 minus x squared dx. V, the integral of 1, is just x. So we get our uv, which is going to be x arc sine of x, minus the integral of v du, which is going to be x over the square root of 1 minus x squared, which we can actually do. It's going to take a U-substitution. So if you let u be that inside function, 1 minus x squared, du is going to be a negative 2x dx. So the dx is going to be du over negative 2x. So our integral becomes that x is over, and we get the square root of u, and the dx gets replaced by du over negative 2x. We account for that extra power of x, and that becomes a negative 1/2 integral of u to the negative 1/2 du. So that is going to be add 1 to that exponent, makes it a u to the positive 1/2, multiply by its reciprocal, and we're going to get the negative square root of, let's see, what was u? The 1 minus x squared. So putting it all together, we're going to get x arc sine of x minus the square root of 1 minus x squared plus c. Oh boy, there you have it.